In this video, we'll explore simplifying radical expressions. Here are some properties that can be very helpful. First, the idea that we can take the product inside one radical and split it into the product of two individual radicals. We can do the same with division as long as the second value is not 0. Sometimes it may be easier to actually take the nth root of a value and then raise it to its power, and that is perfectly legal to do. And last thing is the idea of when we have fractional exponents. When this happens, we know that the numerator represents the power to the base, and then the denominator is going to be the index on the radical for that base. Now, if we have only multiplication and division in our problem of simplifying, we want to separate our interior into perfect and non-perfect roots, and then we can use the associative property to split them up and some of our other radical properties there to simplify the problem. If we have fractions, we need to make sure that the denominator is always left with no radical. So we may need to multiply both the numerator and denominator by some radical to make the denominator become a perfect root. And if you want, you can always work with the exponent fraction form instead of the radical form if that's easier for you. So if I want to simplify the cube root of 40x to the 7th y to the 14th, I first want to separate everything by perfect cubes, since that's my index. And it's always remember that you're taking your exponent and you're going to divide it by your index. So if I look at this, my first perfect cube is 8. That's 2 cubed, so 3 divided by 3 works. When I do x, I need x to the 6th and then times x to the 1st. And then when I do y, I'm looking at y to the 12th times y squared. Now I'm going to group by my perfect cubes and my non-perfect cubes. So I've got the 2 cubed, the x to the 6th, and the y to the 12th, and then I have 5xy squared. So all the terms are there just using the associative property. I can split them into two individual products and then simplify. 2 cubed divided, so my exponent of 3 divided by 3 is 1. Exponent of 6 divided by 3 is 2. And my exponent of 12 divided by 3 is 4. And then I have my cube root. Now say I have this problem of simplifying 6 over 7 times the 5th root of 2. I need to remove that 5th root of 2. I can't leave that in denominator. So I want to say to myself, well, how do I make that become 2? And this is where I would work with it in the fraction form. Because I know when I multiply two values with an exponent, I'm adding the exponents. And it's easy for me to understand, what do I add to the fraction to make it become 1? Well, I add 4/5. And what that tells me is that I'm looking at having to multiply numerator and denominator either by 2 to the 4/5, or if I want to deal with the radical form, the 5th root of 2 to the 4th. So I go through and do that. What this does is it makes my denominator here become 7 times 2. And now let's say, well, I've got 6 over 14, both outside the radical, so I want to simplify that to 3/7. Now, if I have addition or subtraction in my denominator, I'm going to multiply by the inverse operation of the denominator. So if I look at this example, I look at my denominator, I have the square root of 6 minus 4. The inverse operation would be the square root of 6 plus 4. And the reason I do that is because when I have to distribute, I end up canceling middle terms. So let's watch. When I multiply my numerator, I'm going to end up with the square root of 5 multiplied to both terms. And then down here, I'm going to multiply the square root of 6 to both terms and the negative 4 to both terms. And what happens, you see here, is the 4 square root of 6 and the negative 4 square root of 6 cancel each other out. And then square root of 6 times square root of 6 is 6. So I end up with the square root of 30 plus 4 the square root of 5 over 6 minus 16. And that's going to give me a negative 10 in my denominator, so I'm just going to pull that negative out front and put everything else in parentheses.